Hello everyone, I'm Sanmin Kim from KAIST, and I'm going to present our work, Predict to Detect, Prediction-Guided 3D Object Detection using Sequential Images. Sequential images offer several advantages over single image. Firstly, sequential images provide valuable motion cues. Like the image on the left, we can easily find out that the truck is stationary using sequential images, which is impossible with only a single image. Secondly, sequential images can handle occluded objects. It allows us to deduce concealed object or a situation. Moreover, these image streams can be easily obtained in a driving environment, requiring no additional effort. Despite of these advantages, using sequential images inherent some challenges. In particular, moving objects in the scene hinder taking full advantage of sequential images. Since both camera and object are moving in the sequential image setting, conventional method based on triangulation cannot be applied. Additionally, moving objects introduce smearing effects in features, making knife temporal aggregation ineffective. To overcome this limitation, we propose a novel temporal image-based 3D object detection that learns motion cues. In this work, we introduce prediction into the detection framework. Prediction involves forecasting object information in the current frame using only historical frames, while detection leverages current frame as the input. To demonstrate the potential of prediction, we evaluated its performance on Lucene validation set. And surprisingly, as shown in the table, prediction can achieve comparable performance to detection. This result highlights that leveraging prediction scheme can improve the detection performance. Here is the overall architecture of the proposed method. The main idea is to combine prediction and detection in a unified framework. So we first predict objects in the current frame using only previous frames, and then we use this predicted information to refine the final detection. To delve into the details, we begin by extracting class-agnostic heat map from prediction. We then use this heat map to mask prediction result, focusing on the foreground area. And these masked predictions are processed into prediction-guided object queries using a query encoder. We apply the form-over attention on the temporal BV features with the prediction-guided object queries. And finally, detection head decode the spatiotemporal features into final detection results. And our loss function is the summation of detection and prediction loss. We trained and evaluated our model using Lucene dataset. The results demonstrate that our P2D outperforms other models, including baseline models, in both small and large backbones and image size. We also visualize several important cases, and the first scenario is occlusion. In the image, green boxes are predicted results and red boxes are ground truths. In this scenario, vehicles on the right side are visible in the first frame at t-2, but they become occluded by a truck in the following frames. The baseline model starts to lose this occluded object from t-1 and fails to detect all of them at t. On the other hand, P2D successfully keeps track of all occluded objects and does not miss any of them throughout all timestamps. The second case involves moving objects. P2D can detect all moving objects in the frame, while the baseline model fails. This case demonstrates the ability of P2D to effectively detect moving objects. Thank you for watching video and feel free to reach out for any further questions or discussions.